Hello, I'm Stefan Alanis from the University of Tübingen, and I'm going to present our work on iterative superquadric recomposition of 3D objects from multiple views. The goal of our work is to reconstruct 3D objects with superquadric shapes, which allows us to efficiently represent objects of simple parts just from a few views, thus generalizing to arbitrary objects. Suppose we have some views of an object. We first apply an off-the-shelf segmentation model to obtain object silhouettes. Next, we apply our iterative superquadric recomposition method, ISCO, to build the object step by step. In the end, we obtain an object representation by its parts that is easy to manipulate because of its explicit structure. Superquadrics are our building blocks, because they can take on a large variety of shapes from just a few parameters, as you can see here. We use the implicit representation of superquadrics for the shape, and then apply a rigid transformation to arrange them in the 3D space. Let me give you some more details on how ISCO works. We start with a set of images from different views where we also know the camera poses. Our algorithm iteratively adds new superquadrics to the scene and optimizes its parameters using a reconstruction loss as indicated here for the blue shape. For this optimization, we render the silhouettes of our reconstructed object using a differential rendering pipeline and compare it to the ground truth silhouette applying an L2 loss. Importantly, we split the loss term into pixels belonging to the object and those outside of the object. By putting a higher weight on the outside pixels, we discourage the superquadrics to extend beyond object boundaries, thus only covering local parts of the object. After the optimization converges, we initialize a new superquadric around the part of the object that is not covered in our reconstruction yet. By propagating the loss gradient of the object pixels to a voxel grid in the 3D space, we estimate the area of highest error. At this location, a new superquadric is initialized and again optimized. After multiple iterations, we then obtain a complete reconstruction of the object with superquadrics. Here's an example of how ISCO iteratively adds superquadrics when we show a subset here of the iterations. At the bottom, you can see the error estimation in 3D, where reconstruction errors are gradually covered by new superquadrics. The same can be observed for this table and plane, where the main parts of the object are reconstructed first before finer details are represented. We evaluate ISCO on ShapeNet, which covers a large variety of objects. Looking at the IOU results, ISCO performs better than recent superquadric reconstruction methods that rely on point clouds. And it's not far from implicit approaches such as News that fits an implicit surface by training a neural network, which is computationally much more expensive. We also ablate the iterative procedure of our algorithm, which is a key component of ISCO. Without it, superquadrics compete for the same object parts, resulting in worse reconstruction and less semantic relevance of each superquadric. We test how well ISCO can recover semantic parts of an object, as indicated here on the left by evaluating on ShapeNet part. ISCO outperforms other training set free methods such as EMS and NBP, while coming close to methods that use training data at the top of the table. Because ISCO is an instance-based method, we cannot guarantee that the same superquadric is used for the same semantic part across objects. Due to this limitation, ISCO performs worse if consistency between objects is required, as indicated by the C column in the table, but it still outperforms its competitors. Nonetheless, the flexibility of ISCO allows application on arbitrary objects, even when no training data is available, where we can still recover semantically meaningful parts and obtain better reconstructions than competitors as seen here on a CO3D dataset. If you want to know more about our work, please check out our code in our paper. Thank you for your time and attention.